So with the previous video, we concluded the topic of time integration. Time integration is basically a set of tools which helps us do physics-based simulation. And now in this video, in the following lectures, we're gonna see how we apply this time integration to various types of physical objects. So we're gonna look at solids, fluids, and elastic objects. And we're gonna start with the elastic objects today. So the integration techniques we saw before, they're applied universally to all physics simulation. The only difference between the different simulations are really in the forces which come into play and sometimes the discretization of our objects. How do we represent it in a computer? So, for example, we're going to look at rigid bodies where they're going to be represented by one point because they're rigid, and the typical forces are gravity and friction. Elastic bodies, cloth is a quintessential typical example of an elastic body which is used ubiquitous in games and also special effects. In cloth, we have gravity, we have elastic forces, we have friction. And then in the fluids, we're going to have basically the Navier-Stokes equation, which are going to be forces, pressure forces, friction forces, tension forces. So they're going to be more complex type of forces coming into play. So we're going to start with the elastic objects. Elastic objects are objects that when they are deformed, they tend to return back to the rest pose. So when some external forces deforce them, if those external forces get removed, the internal forces push them towards the rest pose. These are called stress. And of course, if we deform them, if I take a squishy toy and I deform it, essentially the internal forces are still there, but they are compensated by external forces, and hence we have the deformation. The geometric deformation, so we have a geometric problem, so the objects are deformed, so the shape of the object is different. This is called a strain. And the forces which result from this change in deformation, the change in pose, the deformation, they're called a stress. And in physics, we have Hooke's law, which says that there's a linear relationship between stress and strain, which means that the more we deform, the internal forces are proportional to how much we deform the object. It's worth mentioning that Hooke's law, it's only correct for very elastic objects. If you have, for example, relatively rigid objects, because if you look at steel, steel can also be seen as an elastic object with very, very small strain, and then the Hooke's law doesn't really apply. So Hooke's law is not really universally applicable, but in graphics it works really well because it simplifies the problem, and for kind of squishy objects, which is what we typically use, they are quite good. Now, this concept of stress and strain, it's a bit abstract at this point because we can only formalize it once we have a discretization. So we're going to look at two types of discretization which typically are used in computer graphics and computer animation. One is a spring system. Essentially, the objects are modeled as a bunch of springs, linear springs, and a lot of closed simulation is done by that. And these spring systems are very simple in some sense. I mean, still you have to implement one for assignment 3, so it's not going to be trivial, but compared to finite element method, which is now on the other side, which is a second way to discretize elastic objects, is much simple. So the finite element method, instead of building, so spring systems build an object using springs. Finite element methods build objects using either 2D elements, such as triangle, shown here, triangle or rectangles, Or in 3D, you have 3D elements, most typically tetrahedral and hexahedral, and sometimes you have prismatic and pyramidal. And so these are essentially generalization of springs in 3D. So the spring kind of stretches in one direction. In finite element methods, these elements in 2D or 3D can stretch in multiple directions. So it's literally a generalization of springs. So let's go back to our simple yet quite used spring model. So put it simply, a spring is a one-dimensional element that can basically be deformed only in one direction. And when it is deformed, it exercises an internal force equal to minus k of delta x, where this is an internal force where delta x is the amount of change, the difference in length, if it was elongated or compressed, and k is the stiffness of the spring. So a stiffer spring has more force, and so on and so forth. So you see, this is where Hooke's law plays into our equation, because the force and the displacement, so the strain and the stress, the force is the stress, the delta x is the strain. It's actually it's the ratio between the two is constant, so they are proportional. So, of course, this force in 1D had the expression you saw before, but these springs are not, even though they are themselves one-dimensional, they're embedded in some other space. So, for example, if we use springs to make cloth, they're going to be 2D. They're going to live in 3D. Or in some examples, they can live in 2D. For your homework, you have a 2D example, but in general, they live in 3D. If they live in 3D, we have to formalize, to express the internal forces as a function of the two endpoints of the spring. So if we assume that the ends of the springs are xi, xj, the internal force is minus k. This doesn't change the stiffness of the spring. But now this is the difference in the change in length of the spring, and this is essentially the norm of the vector between xi and j minus the length of the spring, times, and this here is just the direction of the force. So this first part in blue is the magnitude of the force, and in red here is the mass. So this is the direction. Oh, I want to do it in. This is the direction of the force, and this is the magnitude here. And direction in the sense of vector, of course, this minus sign is going to put it in the other direction, but this is a unit. This in red here, it's a unit vector between xi and xj. And so, yeah. Okay, this is the expression of the internal forces, but are there any other forces? I wait a few seconds for you to think about. Well, if you don't know of the other forces, think about what happens if you take a spring and you let go. If you only consider this force, what's going to happen? Well, it's going to pull back towards the rest pose, but even if it gets to the rest pose, where there's no more forces, it still has some velocity which is going to pull it in the other direction. So it's going to oscillate infinitely. So this is where we have to add some sort of friction force, because the spring, if you pull a spring in practice and you let go at one end, it doesn't oscillate forever. It stops pretty quickly, actually. And this is because the spring is made out of metal, and the metal is pretty stiff, and it has a lot of friction at the structural level, and so it stops pretty quickly. So this we don't model friction very accurately, we just call it a damping force, which is depending on the velocity. So this damping force, it's very similar to a friction force, but we are removing certain um, I mean, we simplified as much as possible. So it's just the velocity times a damping constant, which is this one here. So if we want the system to be more, to have more damping, to more faster go to the equilibrium pose, we put a high number here. So this is proportional to the velocity, right? So the higher the velocity, the faster, the larger the damping force. So in a nutshell, that's pretty much it. So we take these forces, the interior forces of the spring and the damping forces. We can add other things like gravity and wind, especially for the cloth simulation. And then we can plug them in our favorite time integrator and then run the simulation. But I have to warn you that actually using your favorite time integrator is a bit misleading, because if your favorite time integrator is explicit Euler, it's not going to work. There are some problems where the simple Euler methods work, but spring systems and cloth doesn't work so well. So typically you have to use implicit backward Euler, which is what you're asked to do for your assignment. So on that note, I'm gonna go over with you, I'm gonna go over one example, okay? So in this example, we have one spring, which is fixed at one end, x0 bar, and the other end is left mobile. And this is the one that we have to compute the motion of. It has some mass m, which is non-zero, and the spring, we let it, the simulation starts when the spring is at undeformed configuration. So basically, there's no internal force, if you will, at that point. It has no initial velocity, and we also know the length, the rest length of L, and we just allow the gravity. Of course, if we don't have the gravity, nothing is going to move because the velocity of V0 is 0 and the internal forces are 0. There's nothing that makes it move. But if we allow gravity, then this is going to move it down. So so let's see how we formulate it using the in the numerical framework we set up before. So first, the initial condition, right, y0. Remember, we are solving for y, which is the concatenation of x and v. And this is a good example. If this is a 2D example, then x has 2 dimensions, v has 2 dimensions, so y is going to have 4 dimensions. If, for example, this spring lives in 3D, we have 1 degree of freedom, 1 point, but the position is going to be 3 dimensions and the velocity 3 dimensions, so it's going to have 6. If we have a spring system which is embedded in 3D with n points which are free, some of them have to be fixed, otherwise everything is going to fall, but we typically fix some of the points. So if we have n points which are not fixed, the y vector is going to be 6 times n, essentially length. So in this case, y0, it's x0 bar plus 0 minus L, right? Because we go from x0 bar, it's on the same x-axis, but we have to go down minus L. And the initial velocity is 0 here. And we can write also the damping force, it just depends on the velocity, nothing new here. But here I wrote the internal forces using the formula before, but plugging in the variables that we have here, x0 bar and x. So let's see, we said that for springs we have to do implicit Euler, so we took it from before. Yk plus 1 equals yk plus f of tk plus 1 and yk plus 1 times delta t. And I rewrote ft and y here. Again, the ft and y, it's the right-hand side of the Newton's second law of motion equation. So it's going to be v of t and m inverse times f of t. So now let's everything else stays the same. So y0 we did before, and the forces we did before. So now with using this formulas, let's plug in everything and see what we get. This slide explains, puts everything together. So on the left-hand side, you have the standard implicit Euler scheme. The first row gives you the compact formulation. The second row expands it. In the middle here, you have the forces which play a role here. So you have the damping force, which is fairly straightforward. You have the interior spring force, and you have the gravity force. And on the right-hand side, you have the initial values. Now, here in the middle, in the red box, is where the action is. This is where we have to solve for the position and velocity of the point x in our case. So xk plus 1 vk plus 1 equal xk vk plus, and now this is where it's the middle part, the ftk plus 1 yk plus 1. So the top part is vk plus 1, right? This is the velocity at the next time step, so this is unknown. And the bottom part is m inverse times the sum of all forces on k on the point x at time k plus 1. Well, the damping force will depend. It depends on the time, and then because it depends on the velocity at time k plus 1, and the the spring force depends on the position at k plus 1, but the gravity is pretty simple. It's just g times m, doesn't depend on anything actually. So now if we rewrite this system in a more compact way, we have xk plus, the top one is vk plus 1, that doesn't change, but the bottom one, I added all the forces, so it's m inverse times, you have the damping force, which is a constant, times velocity at time k plus 1. This is fine. This vk plus 1, it is a variable, right? But it is in a linear context, so this is simple to solve. But the problem comes here. So the spring force depend on the length of the spring, which is actually the norm, which is a square root of the sum of squares. So here is this force depends on the position of xk plus 1, the position of the next time step. We don't know what this is. This is an unknown, and it's not in a linear equation. This is a nonlinear equation. This has a square root and a sum of squares. And the same problem here at the right-hand side. So this is why this is nonlinear. So we have to solve using a Newton method, like Newton-Raphson iterations. There are others as well, but I am highlighting here in red the equation which basically you have to solve for your homework. But of course that you're not going to have only one point. So to discuss some practical aspects here, typically we have multiple connected springs. This is why they're called spring systems. And some of the points are fixed, some can move. The ones which are fixed, we don't care, right? They're fixed. Some of them have to be fixed, otherwise if you have either if you have gravity, everything falls, or even if you don't have gravity, if nothing is fixed, then the springs will just go to the rest pose. So some points are typically fixed, and then we have x and v, and the x and v, which are the functions we solve for, are actually either matrices or vectors, depends on how you want to implement it. I actually recommend vectors, but the dimensions, the number of variables you have is the same, is n times k. K is the dimension in which you embed, could be 2 or 3. So in practice, you know, when you do 3 animation, it's in 3, but for your homework, you have only 2, and n is the number of variables. Now, there's a couple of more interesting things happening. If a spring is between a variable point and a fixed point, the entire force contributes to the motion of the variable endpoint. But if you have a spring where both ends can move, and this can happen if they're connected to other springs which eventually are fixed. So this can happen. you have to make sure that the internal force is split between these two endpoints. So each of the endpoints, half of the force contributes to the motion. So actually, because of this logic, this makes the differentiation quite difficult because you have to basically have two different cases for each of this situation. And this is going to be tricky because actually you have, when you do Newton's method, you have to differentiate these expressions, and it's not very easy. Uh, if you did this before, you can use some symbolic computation software like Maple, or there are some others, but you can also do it by hand. These expressions are complex, but not that complex. So if you never did it before with a symbolic solver, you can do it by hand. This is just taking simple derivatives like you did in high school. So let's conclude this lecture on springs, saying that the biggest advantage of springs is that they're simple to understand and implement. I mean, yes, you're going to have some hard time implementing them, so they're not trivial, but they're much easier than, let's say, FEM. Also, they're pretty fast, but at the same time, they're limited because only as much as you can do if you have forces in one direction. If you do cloth simulation, cloth has resistance and elasticity in all directions. So to model cloth, you have to have a pretty complex spring system. And for other objects, it doesn't work at all. So the finite element method, which is the alternative of spring system, it's actually much more used in physics simulation, but it's pretty complicated because essentially these elements, 2D elements or 3D elements, they're essentially multidimensional springs. So if you have one dimension, it's pretty straightforward. It's k times the distance, the offset, right? But in 2D or in 3D, it's not very clear what does it mean. So the spring part, how the forces, the internal forces work for 2D or 3D elements, it's actually much more difficult. And it goes from a force-centric view of the simulation to an energy-centric view. Well, this is all for this lecture. It's this lecture on physics simulation, time integration, and springs. It's quite big. I don't know exactly. I'm finishing out the videos. I don't know exactly how long it is. Pretty long. But I hope you enjoy it, and I'm looking forward to see you in class.